All right, how's it going, everybody? We are here on Tuesday of week 7. We're gonna take a look at our second video lecture of the week here. Last class, I've got up on our screen right now where we wrapped up at the end of last video. Last video, we were looking at what we call the empirical rule, also known as the 68, 95, 99.7 rule. Ridiculous name, but also very practical because those are just the only three numbers you need to know to understand estimating some probabilities. What we finished with in the last video is seeing that we can make pretty reasonable estimates of some probabilities associated with the normal distribution as long as we are interested in probabilities associated with whole numbers of standard deviations. So as you can see on the screen right now, when we looked at between 1 and 2 standard deviations below normal, since those were both referencing a whole number of standard deviations, we were able to use this empirical rule to make a reasonable estimate of the probability of that type of event occurring, about 13.5%. Where we closed with last time was looking at this next question here. What was the probability that we see an outcome that is at least 1.5 standard deviations above average? And what we're realizing here is that this is a partial, this is not a whole number of standard deviations right here, and consequently we can't really see a way to use the empirical rule to make estimates that are associated with this. So the empirical rule is very convenient for making very quick estimates, but unfortunately can really only handle discussion about whole numbers of standard deviations. And so what we need to be able to do is we need to be able to compute probabilities associated with the normal distribution when we do not have a whole number of standard deviations associated with that probability. So what we're going to do today is we're going to start with the wrap up to section 6.2, which is looking at using technology to compute some of these probabilities. I'm going to show you guys how to do this in Excel. I'm also going to show you, I don't have a TI calculator to show on screen, but I'll show you what I've got at least typed out some of the key inputs here. And again, there's a significant amount of assistance with the TI calculator available online. One of the other things that I've noticed is that in a lot of the MyOpen math homework, all of the videos that are providing you like a little bit of assistance in how to calculate something, all the people in those videos are using a TI calculator to help you out there. So if you've got a TI calculator, then watching the videos in the MyOpen math homework, I think is a pretty good place for you to get the information that you need to use your calculator associated with that. So I'm going to walk through the Excel computations here today. So what we're interested in doing, again, is we're interested in computing probabilities associated with the normal distribution in the scenarios where the empirical rule won't do it for us, when we don't necessarily have a whole number of standard deviations. So let's take a look at a couple of examples here. We're going to do a couple easy ones, and then we'll do a couple that are a little bit more tricky where we got to be careful. And very importantly, one of the things I want to point out to you guys right now is that we're going to draw a diagram for every single one of these probabilities that we compute. I will strongly, strongly encourage you to draw a quick bell curve associated with literally every problem that you do. This takes next to no time to do, and it helps make sure that you are orienting yourself correctly as to how you think about these probabilities here. So we are going to look at, for our example here, we've got a sort of a generic distribution right here. We're saying some random variable x is distributed normally with an average of 80 and with a standard deviation of 5, right? So we've got our mu, we've got our sigma right there, our average and our standard deviation. I'll just write this in words right here. Average is 80, our standard deviation is 5. What we want to know is what is the probability that x takes on a value less than 72? In this case here, we have been given an x value, a value that is associated with the x distribution of 72. And what we are interested in doing is determining what probability is going to be associated with seeing values that are less than that x value of 72. The reason I've got the statement here in parentheses is if you see at the bottom of our screen, we're going to kind of switch it in the next problem right here. Instead of the next problem, we're going to get our probability as our input, and we're going to want to give x as our output. But we'll get to that in one second here. So let's go ahead and do the most responsible thing here first, and let's go ahead and draw our diagram that is associated with this guy here. So if I am thinking about my normal distribution here, I'm going to draw myself a little bell-shaped curve. I know that we are centered at an average of 80, and I know that if I want to mark just a couple standard deviations out here, that we should be getting like an 85 and a 90 there, a 75 and a 70 here. What we are interested in is the probability that x takes on a value of less than 72. So what I know that I'm interested in right here, here is our x equals 72 line, and I am interested in all of this area to the left. I want to know the probability that our x value will take on a value less than 72. So what I want to do is determine how much area is there underneath our normal distribution curve, less than 72. Right? X is equal to 72, right at that line right there. So our area of interest is that region that is shaded to the left right there. So we are interested in the probability here. I would say that X is less than 72. So what we're going to do is we're going to pop over into Excel and we're going to go ahead and answer this question here. So over in Excel, let me bring up some Excel stuff here. So we're over in Excel. And let me kind of just give the information that we've seen here. We have seen that our average is 80. We've been given that our standard deviation is 5. And we want the probability that x is less than 72 right here. That's the thing of interest here. So we're going to go ahead and we're going to compute this in a very similar way to the way that we did the binomial stuff before. Is that we are going to do equals. Before we did binom.dist for the binomial distribution. Now we're going to do norm.dist because it is a normal distribution probability that we're interested in computing. So as with the last time, we have this stupid little thing right here where you guys can't see it, but right now my mouse is hovering over a list of stuff that's right here. If you did any of your binomial stuff in Excel, then you know what I'm talking about. There's a little list, this drop-down menu right here that's informing me of what my options are right now. I'm going to continue typing out the binom, or the norm, not binom, we're not binomial, we're normally distributed. And as soon as I open up the parentheses here, it's giving me exactly what it wants inside of the parentheses. It's showing x, mean, standard deviation, and cumulative. Here, my x value of interest, my edge, is 72. That's my x boundary. The mean of our distribution is 80. The standard deviation of our distribution is 2. And here, by the way, we are always going to give true for all of the Excel computations that we're going to do here because we are always accumulating a probability up to some amount. Up to 72 is all the locations of interest right here. And so when I hit enter right here, is that really? Or? Oh my gosh. Okay. Let me tell you what's happening right here. All right. So one thing I can see right here, and I'm just going to type this out over here for us. All right. I made a mistake, and I know that I made a mistake. This is actually great that I did this right here. Let's talk through this mistake that I made. I just got the answer of 3.16712 E negative 0.5. So one thing I want to do is tell you, even though I did this wrong right here, we still should interpret this and ask ourselves, how do we know that we're wrong? What this really means right here, when you say E negative 0.5, that's really saying this is given in scientific notation, and this is our indicator to bump the decimal place to the left 5 places. You should notice here the decimal is currently 1 place to the right of the 3. So to move it left 5 places is going to move it 1 place will get us on the other side of 3. The next 4 bumps will introduce 4 zeros. So this should be 0.0000316 or 317, I guess, if I'm rounding appropriately right there. Now, how do I know if this is wrong? Well, this to me would represent, now to convert this to a percentage, this would be a move the decimal 2 places back to the right, and we'd be getting a 0.003%. This disagrees with the empirical rule that I know that we've seen before. Let me pop back into Word over here. I know that here we are within 2 standard deviations, right? 72 is between 1 and 2 standard deviations below normal. I know from the empirical rule that 95% of our results will be within 2 standard deviations. And so we also saw some things over here yesterday, such as the fact that therefore there should be the remaining 5% should be outside of this 95%, right? If 95% is the middle chunk there for 2 standard deviations, then outside of 2 standard deviations should be the remaining 5% of our probability. Since this distribution is symmetric, that 5% will get split evenly, 2.5% and 2.5% in each tail that's out here. So what I know here is that since we are interested in something that is between 1 and 2 standard deviations below normal, I know that my answer is going to be bigger than 2.5% because I'm going to get all the area of 2.5% plus the little bit that's associated with the extra little bit between 2 and 1 standard deviations that we've got right here. So I know that I'm expecting something more like 3, 4, 5%, something like that, and we just got a 0.0003%. So one of the reasons why the empirical rule is really valuable is because it helps you decide if your answers that you're getting from technology are reasonable. Did we just do the right thing here or not? I know that this answer that we just got in Excel seems very extremely small relative to what the empirical rule told us. So now I'm going to go back and I just have my moment of panic there that we're now going to go fix. It looks like I just typed in our information a little bit wrong, right? 72 was the x value of interest, 80 was the average, but I accidentally typed in 2 here for the standard deviation instead of 5 like we were supposed to. Now remember, a second ago we just said we're going to guess. It should be a little bit more than that 2.5%, so maybe like a 3, 4, 5% or something like that. And what do you know? We're getting about 5.5% right there. I can see the 0.0548 as I would round that to, and so it looks like a 5.48% is our answer to this question right here. So let me pop back over into Word and write down our answer here. And so here we did, I'm going to write this one out here, we did equals norm dot dist. It's going to be x mu sigma cumulative, and again we're always going to give true for cumulative in these normal cases. So we chose to do norm.dist. Our x value of interest was 72, our average was 80, our standard deviation when I did it correctly was 5, and our cumulative was true because we are accumulating all the probability up to 72. Anything up to 72 would satisfy our probability of interest. All x values less than 72, we wanted to accumulate their probability there. And so what we ended up finding here was we got a 5.48 out of this guy here. All right. So the other thing that we can do here of interest is that we can, oh, and I've got this written out right here. The other thing of interest here is we could flip this problem around. And number 2, we are given a percentage, 90% of the results, and we are interested in finding what x value is going to be associated with that. So what I am seeing here is we just want to sort of do this backwards. I am going to, again, draw my diagram that's associated with this here. Get out of here, this stuff. My diagram associated with this, I'm thinking to myself, we're still sitting there at our, ooh, see, you're going to get some funky looking normal curves out there, just like I do. 85, 90. Now remember, these are all our actual x values here, not the percentages, right? These are all x values on this axis right here. What I am interested in is finding where we're going to get 90% of the values to be below us, right? If you're in the 90th percentile, then that means that 90% of all responses are equal to or less than your value. So again, I'm going to come back up and look at my empirical rule diagram. When I see this here, what I know I'm interested in is finding the location where to the left of that location is 90% of all the responses. So what I'm kind of thinking to myself here, again, I just showed up here that 2.5% are above, right? So it looks to me here like this guy right at 2, this is about our 97.5th percentile, right? Because this is where 2.5% are above and 97.5% are going to be below. So I'm picturing to myself we should be getting something that's about between 1 and 2 standard deviations for our answer right here. Something in the ballpark of that. I'm just trying to use my empirical rule to sort of make estimates of what I expect for my answer. So based on the empirical rule, it seems to me like somewhere between 1 and 2 standard deviations above normal is where we're going to see 90% of outputs are going to be below it, 10% of outputs are going to be above it right there. I'm just trying to eyeball this right here. So again, we're picturing that our answer should be between 1 and 2 standard deviations above normal. And so I'm picturing for myself that we're thinking that there's going to be something like this guy right there. That's my estimate of my answer. Again, we're picturing here that this should be 90% and that this should be 10% over here. We want to know what x value gives us 90% below and 10% above. What's really important for us to notice here is that in the previous problem we took in an x value and we spit out a probability. In this one we're taking in a probability and we're spitting out an x value. We're doing the backwards computation, also known as an inverse computation right here. So here what we're going to do is we're going to go find our norm stuff in Excel, but we're going to look for norm inverse. We want to do the backwards computation here. Let's pop back over into Excel here. We'll state what it is that we want. Oh, sorry. I'm gonna come back into Word real quick right here and write this out. What we're kind of saying here is, and I want to kind of mimic the stuff that I wrote down in the last one. What we were saying here is we want to know the probability that our random variable x was less than 72. Here, I don't know what I want x to be less than. It needs to be less than some number k. But what I want is I want to be able to say the probability of seeing x is less than or equal to that special number k to be 90%, 0.9. So again, notice here what we didn't know over here, the unknown was the probability in the first example. Here, the unknown is the x value that causes that amount of probability, 90% to be to the left right there. So here we knew the x value, 72. Here we don't know the x value. We're just calling k the special x value that will have 90% of all outputs being to the left right there. So our answer is going to be in the format like k equals or x equals right here, some number. So now let's pop over into Excel so we can actually write that stuff down. Here for our second example, we want to find the probability that x is less than k to be equal to 0.9. That's our statement of interest right here. We want to find what is the special x value that causes 90% of our area to be to the left, as I can see from that less than or equal to our value of interest. So I'm going to go ahead and hit equals. I'm going to start typing. And again, you can't see it, but there's a drop-down menu that just popped up, and I can see all my options. The option immediately below norm.dist, what we used last time, is norm.inv, INV for inverse right there. It's going to do the backwards computation. When I bust open my parentheses, it's going to give me three different things that I need to type in. It's going to first ask me for a probability. That's the 90% that we're interested in here. The 90% of responses are going to be below our value of interest. So this is where I'll give 0.9 for the probability. And then I just want the mean and standard deviation because we're doing normally distributed stuff. Here our mean is 80. Our standard deviation is 5. And remember, we guessed that we were going to get something. Sorry, it's really important that we do these guesses here. I know I'm popping back and forth between screens a lot. When I come back over here, remember, we guessed between 1 and 2 standard deviations, which in this case is between 85 and 90, right? We can see the 85 and 90 is between our 1 and 2 standard deviations. So I'm estimating that I'm going to get something like an 87 or something very near to that, right? Between 85, oh wait, 80, oh yeah, 85 and, yeah, something like 87, sorry. Driving myself crazy here. I'm misreading numbers. So I'm guessing my answer, and this matters because, you know, you guys got to realize we're going to go to our calculator for a ton of computations this semester, and it matters that you are able to like stop and be like, did I type this in right? Is this answer what I was expecting to get? Since we really have to like trust technology here, it matters that we can stop and like make a reasonable judgment of the technology given answers, right? We want to say like, wait a minute, I just got an answer, like in the one that I did wrong, I'm going to go 0.0000317. You need to stop and be able to like assess the validity of that. And the empirical rule, even if we don't directly use it all the time, is a great way for you to like gauge about where your answers might live so that when you do get answers out of your calculator, you're going to be like, totally, that's about what I was expecting right there. And that is going to give you the confidence that you are going to want to have rather than just being like, I don't know, it's a number my calculator gave me. That's not a great way to go through this course, right? So making these guesses really matters. It's going to make you confident that you are doing the right thing. So I'm guessing I'm going to see something about like 87. I don't think it's going to be like exactly 87, but something between 85 and 90. And when I come over here and hit enter in the cell, I'm getting 86.4. I immediately feel excellent about this answer because it's very close to what my estimate was right there. And this is actually great. I'm going to be honest with you guys. I did not do this right before lecture right here to prepare for myself. I really truly am just guessing these values right here on the fly and like kind of nailing them, right? This is feeling pretty good. Here I said 3, 4, 5, I got 5.5%. Here I said about 87, I got 86.4. I'm doing good with my guesses, and my guesses are coming from me understanding the empirical rule. So do that for yourself. Give yourself that favor of understanding how to use the empirical rule, the 80 or the 68, 95, 99.7% rule to help you estimate your answers so that you feel good about what technology tells you. So it looks like we can pop back over into Word here, and our answer was 86.4. Seems like what we were looking for. So 86.4. And here I'm calling that x or k. To me, k is a special x value. It's the one of interest right there. So I'm not too worried about the lettering that we're notating here. And I would write this out, except I forgot that I did actually just type this out down here. So what we did in problem number 1 right there, when we were looking for the probability that x is less than 72 in Excel, you're always going to see the norm dist format like this. This is how you use the norm dist function in Excel. Norm.dist, and it's always going to be looking for the x value of interest, the cutoff value, x value, which is 72 here, and we need to know the average and standard deviation. Just like in binom.dist, you always needed to give it n and p because that's how a binomial distribution is defined. Here, normal distributions are always defined by mu and sigma, so those are always going to be components of the computation. We're always going to give cumulative to be true because we're always going to be computing intervals of probabilities, right, up to 72. And we're going to look at some more of those in a minute. If you're in the TI calculator, this one is a little bit different here. In the TI calculator, it's going to look for lower and upper bounds as well as knowing mu and sigma right here. So the mu and sigma is standard, but notice the TI calculator does this a little bit differently. The TI calculator wants to know what's the lower bound of our interval of interest and what's the upper bound of our interval of interest. We can see from the diagram that we're drawing here that our area of interest in a sense goes to the left forever. Remember in our previous video we discussed the fact that these normal distributions, they cover a vast majority of their probability within 3 standard deviations, covers 99.7% of all the probability, but technically speaking this tail literally goes on forever in both directions. So I want to suggest to the calculator that it should be going, sorry, I'll point my finger in the actual correct direction. I need to flip my screen here eventually. We're really trying to go left forever, but your calculator can't understand values like negative infinity. So what we do here, typically in the calculator, is we give our calculator literally the leftmost number it can ever understand. This is 1 times 10 to the 99th. This is a 1 with 99 zeros after it, but a negative version of that, right? So this is like negative a Google or something like that. So this is the biggest negative number your calculator can understand. So this is saying go all the way to the left for our interval, and up on the right end, our upper bound, our rightmost bound, should be that 72 value. Oh, sorry, I was looking at the wrong picture. Here we go. Here's our correct picture. Our left bound says go left forever. Our right bound says our upper bound is 72 as an x value here. So it's typical if you're using your TI calculator that if you're ever doing just a straight up less than or straight up greater than, that you will use either positive or negative 1e99 to sort of simulate the idea of infinity in a calculator that doesn't have a concept of the number infinity. So you just got to give it a crazy big number to sort of represent a very big number right there. And then again, our upper bound was the x value of 72, which I got, and again, the diagram is so useful for that. That's how I know how to use this lower and upper bound. Average standard deviation, the 80 and the 5 are not super exciting right there. That's just the information that we were given, just like the 80 and 5 right there. Now, when we did our second problem here, find the special value that causes 90% of our values to be to the left of that. We did norm inverse in Excel, and it's always going to take in this probability of interest here, which is the 0.9. Mu and sigma are average and standard deviation. So this is exactly what I just did in Excel to get my answer of the 84 point, or was it 86.4 right there? And fortunately in our TI calculator, the computation is literally the exact same thing, just instead of calling it norm.inv, in your TI calculator. It's called inv norm in the distribution setting right there. And you're actually going to give the literal exact same inputs right there. So in the TI calculator, our backwards computation, our inverse computation, the one where we take in a probability and spit out an X value, those are identical right there, but you will see a little bit of a difference between the Excel and the TI calculator computations right there. But they're going to give you the same numbers. They just take in the information slightly differently. So one thing that really, really matters here is that we understand that these computations are always based on the idea that there is an underlying assumption that the values of interest for us are always associated with areas to the left of the given X value. I set us up with an example right here where our area of interest was to the left of our X value of interest here. If I would have instead stated this as what is the probability that X is greater than 72, then we need to stop and think a little bit more carefully about this. The less than situations are the ones where we can think less. The greater than situations are the ones where we have to stop and pay attention a little bit more here, all right? So these were my sort of like easy examples right here because they worked with the defaults. We need to now be a little bit smarter to look at our harder examples right here. So let's do this here. Adult male height. Let's just give us a whole page for this one right here. So we're going to use this adult male height distribution right here. 68 inches is the average adult male height. 2.5 inches is the standard deviation of adult male height. And super importantly, we're going to draw pictures to go with each of these guys right here. And these are all going to be a little bit different than the previous ones, these three guys right here. So here's how we want to think about these guys. So question number one, what is the probability that a randomly selected male is taller than 72 inches? In this case here, we are really asking the question, what is the probability that X is greater than 72? All right. By the way, notice I maybe should have not set this up this way. 72 was a number that we used in the previous problem, right? We did a 72 right here. But this was based on a different distribution with an average of 80 and a standard deviation of 5. That's not what we're working with here. So this is just a coincidence that we're seeing that number 72 a second time right here. I'm going to go ahead and draw my normal distribution right here. I know that our adult male heights will be centered at 68. I can go 1 and 2 standard deviations in each direction right here to feel out where I'm at. Adding 2.5 to 68 is going to give me 70.5. Adding another 2.5 is going to give me 73. And I'm not even going to mark some stuff over here. I know that I'm interested in our X value being 72. So I can see that this is our cutoff here. That's our X equals 72. Because we're interested in X being greater than 72, we are interested in computing this probability over here. All right. So our issue right now is that if we go to Excel and try and just do this computation like we did before and tell it the X value of 72, it will tell us the area to the left. The default is always area to the left. We want the area to the right. So here's how we should be kind of thinking about this guy right here. I'm going to give myself a little more room for this diagram. The entirety of the area, if we go forever left and forever right, this is the 100% of all of the area. This area is what we want. And so what we can do is this is what we can get easily from Excel. From Excel, probability that X is less than 72. We can get that guy from Excel. So based on the three sticks I've just drawn down here, these three intervals down here, what we can see is this. If I start with everything, what I could do is I could chop off this probability that X is less than 72, and what it should leave me with is the probability that X is greater than 72 right here. All right. So what I'm going to say here is I'm going to flip this on myself and say this is 1 minus the probability that X is less than 72, right? I'm flipping that guy around right there. I'm using a complementary probability to help rephrase this in terms of less thans, because less thans will compute area to the left, and that's what Excel does for me. Excel doesn't have a way to compute directly upper probabilities, upper tail probabilities. It will always, 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 always default to left probabilities here. And so we have to rephrase all of our computations of interest as probabilities with a less than symbol. It's sort of required for doing these things in Excel. So it looks like what I can do then is I can do 1 minus our norm dot dist. It's always going to want the x value first, then mu and sigma, x, mu, sigma, cumulative. Our average here was 68. Our standard deviation is 2.5, and our cumulative should be true always right there. And before I go, I'm going to guess. And it's so smart to stop and guess because you want to be able to feel good about your answers. What I have identified is that 72 is between 1 and 2 standard deviations above normal. It's pretty close to halfway between 1 and 2 standard deviations. And we've actually kind of seen this, right? Halfway between 1 and 2 standard deviations, that feels a lot to me like this about 90% that we were getting before. Notice that the upper tail probability is about 10%. So I'm going to ballpark about 10% is I think where we should be. Again, if we're between 1 and 2 standard deviations above normal, then about 90% is below, about 10% is above, depending on where we are between that 1 and 2 standard deviations. So I think my soft estimate for our answer is going to be something like the 10%. And I got this kind of from the intuition from a previous problem right there. Between 1 and 2 standard deviations above normal, about 10% of our probability is above that value. So let's go ahead and do this guy over here in Excel. So let's switch over into Excel, and I'm going to type in essentially exactly this right here. So over to Excel. We got a new scenario for ourselves now. Now we are looking at having an average of 68, a standard deviation of 2.5, and we want the probability that x is greater than 72, which we are going to say is the same thing as, give myself some more room right here, 1 minus the probability that x is less than 72. We have to rephrase things into less than probabilities to do sensible computations in Excel. So I'm going to go ahead and do equals the 1 minus, and then I'll do my norm.dist. I'll give it the x value of 72, the mean of 68, the standard deviation of 2.5. Cumulative will always be true for our normal distributions. And again, we were guessing that our answer should be about 10% of people will be taller than 72 inches. And here, okay, we were a little bit further off right there, about 5% right there. But I don't think that's, yeah, I mean, that still seems within the ballpark of my responses right here, right? I didn't get like 30%, and I didn't get like 0.02% or something wildly far off from that right there. So I'm seeing about 5.5%, 5.48% right here, it looks like. 5.48% I think is a reasonable answer. And so here we're gonna get that answer here, 5.48%. 5.48% of adult males in the United States will have a height of taller than 72 inches, according to this information here. So again, in this case, it matters that we rephrase all of our statements in terms of less thans right here. Number two, we're going to have to importantly do a very, very similar thing. Right? What is the proportion of adult males that are between 64 and 69 inches. So again, step one is always draw your diagram. I'm going to redraw myself a normal distribution here. I'm centered at 68. I know every standard deviation is going to take me 2.5, so that's going to go 70.5 and 73, although that's not really my edge of interest over there. It's really more like this stuff is what's of interest here. If I subtract 2.5 from 68, it's going to give me 65.5, and then subtract another 2.5, that's going to give me 63. So it looks like our area of interest right here, this is like my 64 right here, right? Mark my 64. All the way up to 69 is what we're interested in. So it looks like this is our area of interest. If we can find this area, then we have found the probability that a randomly selected adult male will be between 64 and 69 inches. So again, what I need to do is I need to make some less than statements that help me out right here. Unfortunately, our current statement has a compound inequality here, right? We are interested in this guy. And so here's the way that I'm thinking about this one. If we went and just individually looked at the probabilities that Excel would give us, the cumulative probabilities for up to 64 and up to 69, what they would look like are these two intervals here. This would be our cumulative up to 69. And this interval right here would be our cumulative up to 64. What we want is this guy. This is our probability that 64 is less than x is less than 69. Right? I can do two individual probabilities to help me out with this. This first one that I've indicated here, this is just our probability that x is less than 69. This smaller one here is the probability that x is less than 64. So what it looks like I can do here is I can find all of the area associated with x being less than 69. That would really give us 100% of the area to the left of 69, including this unshaded part. But I don't want that part to be shaded. I don't want to accumulate this area that's unshaded over here. So what I want to then do is chop off the probability associated with x being less than 64. I don't want that included in my answer here. I just want the parts between 64 and 69. So let's accumulate all the area up through 69, but then get rid of the area that's been accumulated up to 64, leaving us just with the probability between 64 and 69 right here. All right? So we're going to rephrase this guy as the probability that x is less than 69 minus the probability that x is less than 64, right? Accumulate all the probability to the left of 69 and then chop off the probability of up to 64 to just leave us with the probability between 64 and 69. And so it looks like we can do two different norm dists here. This would be a 69. 68, 2.5 true, minus norm dot dist 64, 68, 2.5 true. Right, so get a full cumulative area up to 69, but then chop off the cumulative area up to 64 to leave you just with the stuff between 64 and 69. So let's go pop over to Excel and see what we get here. Notice, by the way, that these are a bit tougher for us to estimate right here. When we get to here, it's a little bit hairier for us to do this. I guess one thing I could do is kind of say we're a little bit above average here, and we're a little bit above 2 standard deviations here. So maybe I just think to myself, like, how much area is between 0 and 2 standard deviations is my like ballpark estimate here. I know that from -2 standard deviations to +2 standard deviations, I know that 95% of my area is going to be within 2 standard deviations. I'm really interested in just like 2 standard deviations below up to 0 above, in a sense, right here is my estimate. It's like half of 95%, so like 47.5%. I also think that this extra area right here is more than this missing area right here. So I'm thinking more like in the low 40% or something like that. I'm just trying to make some ballpark of my estimates using the empirical rule. So 40, 45%, something like that. This looks to me like a little bit, maybe less than half of all the area out there. So about 45% is my guess. All right, so let's go hit this guy in Excel. Over here in Excel, we want the probability that 64 is less than x is less than 69. So I'm going to say equals, and then here I'll say probability x is less than 69 minus the probability that x is less than 64. And here we can do equals norm.dist 69, 68, 2.5 true minus a whole second norm.dist of 64, 68, 2.5 true. And again, our guess was about 45%. Ooh, 60%. Okay, a little bit more than I thought, but I think I can see the reason why that's going to be the case right here. So let me come back to a word over here. I guess I can see why this extra area right here is significantly more than this area that we have missing in this chunk that's right there. We accumulated kind of actually quite a bit right here in this extra chunk right there. So that's quite a bit higher than my guess was right there, but I still think that I can believe that to be a little bit more than half right there because we accumulate so much more area near the average than we do out here in the tails, right? There's a lot less height that's going on out there. So I think that my guess here, maybe my guessing skills are a little bit off right here, but we are finding our answer here to be 0.6006, leading me to say 60.06% of all adult males will be between 64 and 69 inches. All right. So let's do the same thing here. We got one more of these to do, and then we'll pick up with our chapter 7 things here. For our last question of our last little toughy ones right here, we're going to do a flipped version of our inverse computations here. My height is such that only 8% of adult males are taller than me. What is my height? The very important thing that you need to recognize in this question here, and by the way, this is really hard for me to directly think about without drawing a diagram. I really am going to encourage you to draw lots of little normal distributions for all these problems here to help you make these estimates. We're centered at 68. We've done this a couple times now. 70.5, 73, subtract 2.5, 65.5, 63. We are interested in finding the location on here where 8% are taller than me, right? So that might be something like right there, right? We're kind of thinking that there's got to be some place out here where there's 8% here. And if there's 8% in that direction, then that must mean that there's 92% to the left. That's really important that we identify that there's 92% to the left because all of our Excel computations are always going to deal with area to the left. So 8% is not going to be the value of interest in this problem. 92% is going to be the value of interest in this problem because it matters that we are always thinking about areas to the left. I really truly do want that stuff that's right there out to the right. But to get that, I need to really rephrase this question as saying, if 8% of people are taller than me, then 92% of people are shorter than me. And it has to be the less than statement that we're interested in here. Oops. 0.08. Then we want to rephrase this as the probability that x is less than k is equal to 0.92. So the important thing to realize with this one is that even though the problem states the number 8%, 8% was the upper tail area, and Excel is always going to deal with left areas, not right areas relative to our location of interest. So it matters that we stop and draw the diagram and then say, if 8% are above, then 92% are below. And so this should now be my norm.inv. The probability of interest is where 0.92, 92% are below this location, our average, our standard deviation, and we'll be able to get a result. I'm expecting something, I think, like in this ballpark right here. I think between 70.5 and 73 seems vaguely reasonable to me. I think it's going to be closer to more like 70 over here, though. I think we're going to get something close to 70. ish, make my guess here. So let's pop over in Excel and see what we end up getting for this guy here. We want the probability that x is greater than k being equal to 0.08. This is the same as the probability that x is less than k is equal to 0.92. We flipped it around right there. So I'm going to do equals norm.inv, probability 0.92 to the left, mean 68, standard deviation 2.5. And here, my guess was 70-ish. I'm getting 71.5. I feel pretty good about my guess right there. I was in the ballpark of where I expected to be. Notice, by the way, if you do this the wrong way, then you would have done norm.inv 0.08, 68, 2.5. And we're seeing here, oh, I didn't press equals in front of it, so it just didn't do anything. Equals norm inverse. When we do this, we're getting 64 inches. And so, again, here you should stop and say to yourself, if I'm 64 inches tall, if I'm 5'4", does that mean that only 8% of people are taller than me? And hopefully you're able to stop and reason with yourself and say, that doesn't make any sense. Definitely more than 8% of adult males are taller than 5'4", so that can't quite be right. It looks like that is representing our boundary for our lower 8%, not our upper 8%. I think it would be reasonable to say 8% of adult males are shorter than 64.5 inches, right? 4.5. So there's our wrong version. And again, you should be able to look at your answer and stop and be like, does that make sense in the context of the problem? Does that agree with the diagram that I drew? So it looks like our answer here is 71.51 inches. So back in Word here, 71.51 inches. I'll put some units on that since we've got them here. So using Excel for these things hopefully is going to feel to you very similar to it did with the binomial distribution. But very importantly now, we've got to really make sure, and this was the case in the binomial, we just didn't talk about it as much then, but really make sure now if you're using Excel, you have to rephrase things in terms of less than statements. Every technology that ever computes any probabilities ever always does left areas, accumulating from the lower up until some boundary of interest. So drawing your diagrams is going to be super practical for you to help keep those things straight in your head. Do you just get to do a straight up probability computation, or do you need to flip this in some sense? Do a 1 minus if we're computing the probabilities. Find the opposite percentage if we're doing an inverse probability. Stuff like that out there. So pay attention, and the diagrams are what save you here. Drawing this little sketch is what helps make you be a reasonable and sane person that can interpret these things. You noticed I made guesses for all of these things right here. Man, that looks like I misspelled guess, but that is my U and my E right there. Anyway, make your guesses. If you get something that's wildly far off from your guess, then you should either go and realize that you did a computation wrong, or maybe stop and realize that maybe you made your guess wrong. I had some pretty close guesses today and one kind of a little bit far guess today, but I talked myself into it being okay. Make the guesses for yourself. Those things, I think they really do matter right there to kind of give you the confidence that you want to feel for these things. So that's my wrap up for our technology. Look at our things right here. I am going to introduce our section 7 stuff, but I don't think we're going to get terribly far with it. I kind of anticipated that this week with the homework. So the MyOpen Math stuff is almost exclusively covering up through this content right here. I knew that we weren't going to quite get into all of our chapter 7 stuff this week, and that's okay. We'll kind of pick up with some more of the parts of that next week right here. I do want to show you some really cool things that are going to happen here with our with some of our chapter 7 items right here though. So let's go ahead and take a look at some of this. So let me save this guy. Let's bring up our new, there we go. Awesome. Some days this stuff does just work out just like the way I want it to. All right. So that was all we were really going to talk about there in chapter 6. In chapter 6, the only other sections that are out there are just kind of like unit project things like that. So just the introduction to the normal distribution, the standard normal distribution with an average of 0 and a standard deviation of 1 is going to be very practical for us here in a minute. We're going to see why we like that guy there. We're going to see some of that in Excel. There's going to be some more new Excel stuff in here, but it's stuff that's going to be easier. It's going to be a simplified version of the previous stuff here. So the deal is that I've kind of been shouting at you guys all semester that the normal distribution is going to end up being the most useful distribution that we discuss all semester. One of the reasons why that's true is because a huge number of things are normally distributed. Tons of things in biology are normally distributed. Human heights, arm spans, pinky lengths, eyeball diameters, heights, not weights. Weights are right skewed. It's easier to be extremely heavy than it is to be extremely light. Wingspans of birds, average femur lengths of elephants. All these things very closely follow normal distributions. Um, Weights of droppings of animals. If you go collect bat guano and stuff, you will find that each individual weight of a poop is going to follow a normal distribution. Like things are normally distributed significantly in biology, lots of other places as well. So on the one hand, tons of things naturally follow normal distributions. On the other hand, there's tons of things that don't individually follow normal distributions, but what we're going to learn in chapter 7 is that collectively, averages of non-normal things will actually follow a normal distribution, which is very strange. And I've got some technology graph stuff to show you here to kind of help convince you of this. The central limit theorem is what's going to tell us that collectively, averages of non-normal things are still going to follow a normal distribution, which is super interesting here. So we want to look at two scenarios to help us get some intuition about this. By the way, CLT here, the central limit theorem. It's the central limit theorem because it says that everything kind of ends up being normally distributed when you look at large groups of objects. So we're going to look at one normally distributed example, adult male height, and we're going to look at one non-normally distributed example, rolls of a die. I'm hoping today that I'm going to get through sort of the concept associated with this, and that starting at the beginning of next week, we'll look at the computations that are associated with this. All right. So we're back in our adult male height scenario here. This is the distribution that you've seen more than any other this semester, I think. Adult male height, average height of 68 inches, that's 5'8", standard deviation of 2.5 inches. So what we want to just talk through, just verbalize our way through. We're not going to directly do any computations here. Let's just get a feel for what we think will happen if we do some sampling associated with adult male height. So let's look at a few scenarios here. And before we do any of the answering here, let's look and see what the three scenarios are. Scenario 1, I randomly sample a single person. I randomly sample 5 people and look at their average height. I randomly sample 100 people and look at their average height. These are the three things we want to compare across right here. So I'm going to randomly sample one person. On average, what is the expected height of that one person? Now, I know that this one person could have quite a bit of variability in their height, right? It could be that when I randomly sample one adult male from the United States, I could just get Shaq. It might happen that I get somebody that's actually like, what Shaq is like 79 inches or something crazy like that. Like he's a huge dude. I think he's actually even taller than that, right? But what we think is that out of all the males, on average, our average expected height that we expect to get for any one person would be the average height of all people. It's the most likely thing to see is our expected value, right? This is just like we say, what's the expected value on a roll of a die? It's 3.5. We're never going to get a 3.5, but it's the closest thing to the middle that we could ever possibly see. So what's the expected value in height right here? Well, 68 inches. That's the most likely scenario for the outcome of one person's height. What is the probability that that one person that we see has a height taller than 70.5 inches? Well, I'm actually going to, this is the one like sort of bit of computation we'll do here. As we've just drawn this diagram a whole bunch of times, right? I've got my average at 68. Notice that 70.5 is exactly one standard deviation above normal here. So I'm going to mark my diagram like this. 65.5 goes there. What we know is that this interval right there covers, let's see here. Yeah, thank you. Oh man, things are playing nice with me today. That is nice. This is our middle 68%, according to the empirical rule. What that means to me is that these two outer chunks out here have to take the rest of the 100%, right? So if we do 100 minus 68, that's going to be giving us the remaining 32%. That 32%, because this is a symmetric distribution, is going to be split evenly into these two tails, right? So it should be that 16% of people are more than one standard deviation below average, and that 16% of people are more than one standard deviation above average. So I'm thinking here, 16% is the probability that that person is going to be taller than 7.5 inches. I got that from the empirical rule right there. The middle 68% covers one standard deviation from average. So the remaining 32% gets split up into the two tails. So that's 16% per tail. 16% of people are more than one standard deviation above. 16% of people are more than one standard deviation below. That's exactly the answer to my question right here. So now we want to just ask the exact same questions for scenario 2 and 3, but the only difference is that now we're going to sample 5 people and look at their average height. So now what you should be picturing is, just imagine that I gave to the entire class that your homework assignment is to go out and take a random sample of 5 people. What I don't want you to do is come back and tell me 5 heights. What I do want you to do is you take the average of the 5 heights that you got and just tell me the average. And I'm going to collect these 70 averages from all the students in our class, right? So even if there's 70 students in our class and it's 5 people per student, that's 350 people that have been averaged or sampled, but I'm not looking for all 350 outcomes. I am looking for the 70 5-person averages from each of you guys. I'm never going to see the 350 individuals. I'm going to see the 70 5-person averages. What do we expect our average height to be for the 5? And again, we're talking about one of these 5-person samples now. If I take a 5-person sample, on average, what do I expect their height to be? Well, if the average height of all people is 68% and it's symmetrically normally distributed, then I would expect that if I took a sample of 5 people, then the most likely average height to get for them is going to be 68 inches still. That really hasn't changed. The average of an average should be the same value, 68. But this next question is going to be a bit different. What is the probability that their average height is taller than 70.5 inches? What is the probability that they are, on average, 5 people have an average height of more than 2.5 inches above average? Well, that seems a little bit weird to me now, because now I'm kind of thinking to myself, now I'm picturing to myself, if I'm going to sample 5 people and find their average height to be at least 2.5 inches above normal, then kind of what I'm picturing out here on my normal curve is that, there's my 70.5. What I'm going to need to do for my 5 people is kind of get like 5 samples that are like all about right there, right? That would be my 5 people that I sampled. That would be like my X0, X1, X2, X3, X4. I might call those guys my 5 samples that I took right there. That seems pretty unlikely to me that I'm going to sample 5 people and see. I kind of basically am going to need them all to be a bit above average, probably, unless I get like Shaq and a bunch of normal people. That's one way that could happen. But it seems unlikely to me, because it seems like in this scenario, I'm not just looking for one person to be a little bit above average. I'm looking to get 5 out of 5 people probably being above average. And that seems pretty unlikely to me, right? That's not like saying, did you roll a 5 on a 6 on a die? And instead, that's like saying, did you roll 5 dice and get all of your rolls to be a 5 or a 6? That's pretty unlikely right there, right? It's much less likely because we're looking to see a group of things deviate collectively from the mean right there. So I'm going to say here, not sure, but definitely less than the 16% we saw before. Right? And we will get this calculation. I might not get to this today, but if we don't, this will be what we pick up with next week right there, is the actual computation to compute this number right here. So the point here is, maybe it just so happened when I took my random sample that I accidentally just snagged the basketball team. And then I should probably expect to get, I think it's perfectly reasonable to think that if you are currently on a basketball team, the average person on a basketball team is probably taller than the average person in general in the United States. It's just a thing. Taller people play basketball, right? So maybe I accidentally just sampled the basketball team right here. But again, you should see that it seems pretty unlikely that we're going to sample like 5 people that are all above average collectively, that not one person was below average, because that should be 50% of all people, right? Scenario 3 now. Now I'm going to sample 100 people. What on average do we expect to get for the average of 100 people? So now in this case, I'm saying, now your homework is every student in the class needs to go take a random sample of 100 people. All 70 of you are going to sample 100 people. And again, I don't want your 100 individual responses. I want you to sample 100 people. I want you to find the average, and you're just going to report the average back to me. In this case, I'm expecting your average to, again, be really near to the overall population average of 68 inches. What is now the probability that our average height is taller than 70.5 inches? Holy cow, does this seem wildly unlikely to me. It's okay that if, and I'm just picturing like aliens coming down to Earth and like abducting a person so that they can do some studies on humans. It might be the case that the aliens just accidentally abduct Shaq. It might happen, and they're like, it seems like this species is mostly like 7'8". That might just happen that they accidentally, it just could happen that they get a very, very, very rare sample if it's one person. But if aliens are going to come down and just randomly select 100 people to study humans, what is the probability that they just happen to select 100 people that are well above average in height? That seems wildly unlikely to me. It seems to me like this probability is extremely unlikely, right? So I'm again going to say not sure, but this seems very unlikely. Right? And the way that I like to phrase this non-statistically is, it's easy for one person to be weird. That's not that weird for one person to be weird. But if you randomly select 100 people and all of them happen to be weird in the exact same way, that's weird. That's an improbable event right there. And here, I'm not trying to talk about people being weirdos. I'm just trying to talk about, and I mean, I'm taller than 70.5 inches. That's not that weird. This is 5'10" and a half right here. That's not that strange. It's not like you're a total weirdo, right? But again, it's easy for one person to be weird. I mean, we live in Humboldt County, plenty of weird people here, right? And Humboldt County is now a bad example for my follow-up statement. But if you were to randomly select 100 people and they all happen to be weird in the exact same way, that's pretty weird. That's a very unlikely event to see. And the larger and larger our group size gets, the stranger it would be to see all of them be different, to deviate from average in the same way. Right? So here, what we've seen with our answers, and man, when I say very unlikely, like holy cow, do I need to like underline that 4 times? That seems incredibly odd that we would randomly sample 100 people and to get their collective average to be very far from the overall population average of 68 inches. So our answers here suggest 2 things that are super importantly related to super important theorems. Thing 1, our confidence that the average height of the sample, x bar, this is our sample average, will be equal to the population average should increase as our sample size increases. I know that when we just sample one random person's height, they're realistically probably aren't going to be 68 inches, right? They're probably going to be a little bit above or below. But we know that if we sampled lots and lots and lots and lots of people, we would expect it to be more and more likely that our sample average is converging on the overall population average. Because honestly, if I took a sample of 50 million people's heights, that's a sample still, a sample size of 50 million adult male heights. But realistically, in the United States, there's only like 115 adult males or something like that, right? So like now I've taken like half of the entire population. It had better be that the average I get is basically nailing the overall population average exactly, right? So kind of our general statement here is that the law of large numbers says as your sample size gets bigger, you should see your sample average get closer and closer to the overall population average. It might be that if you have very small sample sizes that your outcomes deviate quite a bit from the expected value, but as your sample gets larger and larger and larger, it's more and more likely to be representative of the true overall average from the population. And so as n gets bigger, our mathier notation for this would be as n approaches infinity, our sample average approaches our population average. The bigger our sample size gets, the closer our sample average should be to our population average. It should be more likely that we're very, very close to that true population average. So this is a statement about the fact that we said 68 inches 3 times. But I'm more confident in scenario 3 that we'll get something close to 68 inches because we had 100 people being sampled than I was in scenario 1 that we'd be getting 68 inches with only one person. This is still the correct answer here. Our confidence is just lower that it's going to be nearer to this. Here, 68 is the correct answer, and we're more confident that we're going to see something very close to 68 because we sampled a larger number of people. So while there probably were some very tall people in here, there were probably average-wise canceled out by there also being some very short people in here. That's just how normal distribution works. It's equally likely to see unlikely events in each direction, right? We have a symmetric distribution. So that's kind of our statement number 1. as our sample size gets bigger and bigger, our sample average should get closer and closer to our population average. Our slightly more important statement for today's topic is, for our wrap-up topic here, is as our sample size grew, we agree that it will become more and more unusual to find a sample average, X bar, that is far from the mean. All right? This is saying the bigger your group size gets, when they're randomly selected, the more unusual it would be for them to all deviate in the same way, for them to just happen to all be taller than average. That would be really weird. It's not unusual for a single member of a population to deviate from the mean, but it's very unusual for a large sample to collectively deviate from the mean in the same way, for them to all be taller than average. These two statements that we've just made, statement 1 above and statement 2 right here, we weren't really talking in these statements about individual males' heights. What we were really talking about here is the distribution of average heights depending on the number of people that we sampled. So we've been given that the distribution of X, if we call a random variable X somebody's heights, the distribution of an individual male from the population, we always notate our normal distributions this way. In our case, we had an average of 68 and a standard deviation of 2.5 inches. But what we're seeing here is that the central limit theorem is going to suggest to us it's harder to deviate when we have larger and larger groups of people. So we're expecting our standard deviation of the average of a group to be smaller than the standard deviation of one individual. The bigger the group size gets, the smaller our standard deviation is, the harder it is for us to deviate from average. So our central limit theorem is going to tell us, and by the way, I want these two on the same screen at the same time. I'm just going to hit enter here so I can make that happen. An individual is going to have a normal distributed an individual X, notice super importantly, notationally, this is just X right there, is distributed normally mu sigma. If instead we're talking about how are the averages distributed, right? Again, if I assigned all 7 of you to go out and sample 100 people, all of you would report back to me an average height. We could then graph all of the averages that we would see rather than the individuals. I expect the averages to deviate much less from average of 68 inches because it's hard for groups of 100 people to all collectively deviate from the mean in one direction. Right? So I'm expecting my standard deviation of an average of a group to be much smaller than the standard deviation of just one individual. One individual can be weird. Groups, it's hard for groups to all be weird in the same way. So I'm going to see a smaller standard deviation. We can see this smaller standard deviation because rather than just using our standard deviation sigma, we're dividing by the square root of our sample size. That's because we're doing a division. We're now going to get a term that is smaller than what we previously had for our standard deviation. So what I'm seeing here is that how are our averages distributed, our group averages distributed? They're still going to be centered at 68. They're still going to have an average expected grouping average of 68. But our standard deviation is smaller because groups have a harder time deviating from average than individuals do. Right? So it looks like in this case right here, by the way, the square root of 100 in this case is a nice clean value of 10. So it looks like here we would be getting that an average group would be, this is 2.5 divided by 10. And that would just be giving me 0.25. So you should notice now in this case, this whole getting a 70.5 now in this case. Oh wait. Okay, yeah, I was just gonna make a problem right there. I've got these typed out right here, so let's do this guy right here. So again, the point is individuals are going to have an easier time deviating than groups. This is X bar. This is the average result of having sampled N people. The more people you sample, the less likely it is, the smaller standard deviation we're going to have of deviation from that same mean right there. So this is telling us about the sampling distribution of the sample mean. We're taking a sample and we're computing the mean of the sample, the average. We want to know how those averages are going to deviate from average. It's going to have a more difficult time deviating because it's a group of people, a group of whatever it is out there. And so we should be getting smaller standard deviation terms. The standard deviation term should be smaller and smaller and smaller as n, the number sampled, gets bigger and bigger and bigger because it's very difficult. If you were to sample like 1 million people, man, if you didn't get basically exactly 68 inches, my mind would be blown, right? The bigger our sample gets, the harder it is for it to deviate from average, and we're seeing that with a smaller standard deviation term here. So let's answer a few questions here, and I think that answering these three questions will probably basically be how we wrap it up here today. And by the way, this will include a little bit more technology computation here. So suppose I take a sample of one person and find their height. So notice here, this is not actually our group scenario. This is still our old scenario. We're interested in the probability of the height being taller than 70.5 inches. How many standard deviations is this sample above normal? And it's a sample of one right here. That's why I put sample in quotes. What's the probability of this occurring? Well, I now know here that I have that x is distributed normally, 68, 2.5. With n equals 1, I can say that my average, and notice here, I'm doing a bunch of trivial work right here because the average of one person is just the one person. But I do want to show you here that this will work out to be the exact same. This should be our standard deviation of the individual divided by the square root of the sample size. Well, the square root of 1 is just 1. So that was trivial right there, right? So now I can stop and do my z calculation. How many standard deviations is this above average right there? Z should be x minus mu over our sigma. But in this case here, our sigma is going to be associated with our collective average right here. So actually, I'm going to go ahead and give that an x bar right there. And I'm going to call that our sigma sub x bar to make sure that we're not confused about what this guy is right here. And in fact, I should even just change this up here. Or rewrite this as x bar is distributed according to the normal distribution with mu and sigma sub x bar. That's what I'm talking about with this guy right here. Sigma sub x bar being sigma over root n. It's the standard deviation of the sample average. So in this case here, and notice again, I'm kind of doing the trivial example right here. 70.5 minus 68, 70.5, not 7.5. 70.5 minus 68 over the 2.5, that's our standard deviation. We're just getting 2.5 over 2.5, and that's giving me a z of 1 right there. So what I want to know is the probability of being taller than 70.5 inches. That's the probability that z is greater than 1, which we have just learned that we want to rewrite as 1 minus the probability that z is less than 1. So let's pop over into Excel and see that it's actually easier to do these things in terms of z than it is in terms of x. I've determined that having one person be 75 inches is one standard deviation from average, but we're going to see some different results in the upcoming ones right here. So I'm going to pop back over to Excel, and now I want to use my standard normal distribution here. We have that we want the probability that z is greater than 1, z, not x, which we are going to say is equal to 1 minus the probability that z is less than 1. We flipped it around. So I want you to notice here that there's a different and easier computation we can do for the standard normal versus a generic normal. Now that we've standardized this, it's understood that our average is 0 and our standard deviation is 1, and once we're into z-score land. And so here I can do equals norm, but you should notice, and again, I've got a drop-down menu. My mouse is hovering over it right now. You just can't see it. You'll see it when you go to type this in. Rather than just norm.dist, the top four things I see here are norm.dist, norm.inv. Those are the two we've already used. There's also norm.s.dist and norm.s.inv. The .s is referring to standard normal here. And so I'm going to use the standard normal computation here. When I open this, it only gives me two things, z and cumulative, because standard normal means we have converted everything into a standardized place where z-scores are always distributed with an average of 0 and a standard deviation of 1. So all it's asking me for here, and once again, there's a little helper window that just popped up right here that I'm hovering over, that you can even see my mouse changing as I hover over the parts of it. The only things it wants from me are z and cumulative. My z-score here is 1. Cumulative is always going to be true. And I just realized I forgot to do my 1 minus right here. So I need to stick that in. And this is telling me it looks like the probability of being more than 1 standard deviation above normal, 0.156 or 0.1587 if I'm rounding, 0.1587 is my answer here. So let's go back over to Word, 0.1587. Give myself a little more room, 0.1587. Over here we're getting 0.1587, and so this is a 15.87% chance that we will be taller than 70.5 inches, right? I computed my number of z-scores, and I computed the probability in the standard normal distribution because we converted our x information into z information. Our x information was this stuff. Excuse me, our x information was this stuff, x bar information. Our z information was just about the standard normal distribution because we're in z land. Being in z land means you have less stuff to keep track of. So if we do this computation first, we're helped. Right? So let's do another one of these here. Suppose I now take a random sample. So now this is where it gets interesting right here. I'm now going to take a random sample of 5 people and find their average height. We're interested in the probability of the average height of those people being taller than 70.5 inches. That's going to be harder, right? It's harder for a group of people to deviate from average. Right? So in this case, again, we're starting with x being normally distributed, mu sigma. That's x is normally distributed 68, 2.5. But now our sampling distribution of the sampling mean is going to be distributed as mu sigma over root n. In this case for us, that's x bar being distributed normally according to, that's going to be a 68. But this is now going to be 2.5 over the square root of 5. This is us saying x bar is normally distributed with an average of 68. I'm going to go to my calculator now and ask my calculator, what's 2.5 divided by the square root of 5? And I'm getting 1.118. And by the way, keep decimals on your standard deviation. Don't chop this too far off. 3 decimal places at least, if not more. But again, I'm getting 1.118. You should notice that we have a much smaller standard deviation than before. Right? This is my sigma sub x bar right here. Because it's harder for a group of 5 people to deviate from average than it is for 1 person to deviate from average. So I'm going to go ahead and, as requested, how many standard deviations is this sample above average? Well, I'm going to do my z equals x bar minus mu over sigma sub x bar down here. In this case, this should be, I'm going to get the 70.5 is what I'm interested in my average being. 68 is my known population average. But now 1.18 is really my standard deviation of a sample mean here because it's harder for groups to deviate than individuals. I can compute my z-score here then. I'm going to go to my calculator. Well, I can see that I'm going to get up on top. I can at least write this as 2.5 over 1.118. And if I go to my calculator here, 2.5 divided by 1.118 is 2.236. Before, when we do 1 person being 70.5 inches, that was 1 standard deviation away from the mean. Now when we're talking 5 people collectively as a group, if 5 people had an average height of 70.5 inches, that would represent a result that is 2.236 standard deviations away from the mean, much further from the mean. This is going to be a much smaller probability of interest here. So we can go ahead and compute this guy as before. We're doing now our probability that our z value is more than 2.236 is going to be 1 minus the probability that our z is less than 2.236. And so we can go ahead and compute this guy in Excel. And then we'll do one more and we'll call it a day. And we want to see how crazy unlikely this stuff gets here. So I'm going to pop over to Excel, do this guy here. In Excel, we now want the probability that that z is greater than 2.236 which is equal to 1 minus the probability that z is less than 2.236. I'm going to go hit this guy with equals 1 minus norm, because I'm doing a standard normal, because I'm talking about z stuff, norm.s.dist. What's my z value of interest? 2.236. And cumulative is always equal to true. And this is telling me a much smaller probability. Looks like there's only about a 1.27% chance that we would sample 5 people and see their average height to be 70.5 inches. Right? So here, 0.0, so I'm coming back to my word now, and I'm seeing that this was, we got a 0.01268, I guess, or I'll just round this to a 1.27% chance that we would see 5 people have an average height of 70.5 inches. So let's go ahead and do this one more time right here. And I'm going to do one additional computation in Excel to show you exactly how these pan out. And we'll go ahead and call it a day after this one here. And we'll look at, so notice the next upcoming topic is this central limit theorem idea of getting smaller and smaller standard deviations as we take larger and larger group samples. Applies to non-normal things as well. That's where we'll pick up next video here next week. So again here, we're starting with x being normal 68, 2.5. We are going to find x bar, in this case, to be normal 68. But here we're going to take a random sample of 50 people and find their average height. What's the probability that their average height is going to be taller than 70.5? We're going to get a crazy tiny number for this. This is going to be wildly unlikely. I'm going to do my 2.5 divided by the square root of 50. And so this is going to tell me that x bar is normally distributed as 68. And I'm going to go to my calculator again. I'm going to do 2.5 divided by the square root of 50. Holy cow, 0.3536. That is tiny. So that's a very small standard deviation now. We started with a standard deviation of 2.5, but when we take groups of 50 people at a time, it's much harder for 50 people to deviate as a group. So there's a smaller standard deviation according to their group average than there is for individuals from the population. So this is going to allow us to compute a z-score here, and I'm expecting a pretty big z-score. I'm expecting 70.5 inches to now be very far from average when we're talking about groups. So we're still interested in the 70.5 minus the 68. But now we're dividing by this 0.3536 right here. So I'm going to go to my calculator and see what I'm going to get for this z-score here. 70.5 minus 68. 2.5 still on top, divided by 0.3536. And that's telling me 7.07. Holy buckets. Oh my gosh. 7 standard deviations away from normal? That's ridiculous. So let's equate some probabilities here. Shaq, personally, individually, isn't even 7 standard deviations above normal. So here's what I'm saying to you. It is more likely that you would randomly select one person from the population and they are taller than Shaq than it is that you would select 50 people and find their average height to be 70.5 inches. And I'm taller than 70.5 inches. It's hard for groups to deviate from the average collectively because they would all have to be above average to be getting that pretty much. Now, there could obviously be a few below average out there, but we need to be heavily weighting things towards the above average scale of things. So again, Shaq is like 6 standard deviations above normal in individual height. 50 people having an average height of 70.5 is 7 standard deviations above normal. So this is more unlikely of an event that you would take this sample of 50 people than it is that you would take a sample of one person and get somebody of Shaq's height. That's ridiculous. This is going to be a minuscule probability here. So we are now interested in the probability that z is greater than 7.07, which is going to be 1 minus the probability that z is less than 7.07. And I know that I'm going to be getting some scientific notation over here from Excel. So for this next guy here, we want the probability that z is greater than 7.07. is equal to 1 minus the probability that z is less than 7.07. We're going to do this as equals norm dot s for standard, because we're in z dot dist. It's going to want our z value, 7.07. Cumulative is going to be true, always. And look at this. It's literally just telling me 100%. I wonder if I make this bigger, it'll... Nope. Okay. So it's basically 100%. It's not truly 100%, but this, I thought that if I would make this bigger, it would give me something. It's okay. This is realistically going to be more like something like 99.9999999% chance right there. It's not truly a 100% chance because this could happen, but this is insanely unlikely here that we're going to get this to the point where Excel's precision can't even measure the difference between the true answer and 100% right here. So essentially... Oh my gosh. I forgot to do it. I see why Excel is doing this to me. I forgot my 1 minus again right here. This is the probability that we'd see something within, like less than 7.7 standard deviations. That's like everything. That's 100%. We're looking for the probability that we see something more than 7 standard deviations above. That's going to be like 0%, right? So when I do my 1 minus, maybe now it's going to give me, there it is, 7.47. Okay, sorry, let me pop back over here. I'm blown at the end right here. When I switch this now to the 1 minus, like it should have been, because I just forgot the 1 minus in there when I did it, it's giving me this incredibly small number. This would be 0.12345678910111277, which is equal to 0.1234567891077%. That's the probability of seeing the thing that we're looking at right here. I'm just going to copy this into, yeah, I guess I'll say this right here. This is going to be essentially no chance is what we're saying right here. And this is about equivalent to the proportion of humans on Earth that are taller than Shaq. In fact, it's a little bit smaller than the proportion of humans on Earth that are taller than Shaq right here, in the ballpark of that, right? There's a wildly unlikely event right here. 7 standard deviations from normal, that's insane. So, as my very last thing for the day, I just want to back up and show you something else with our one last computation here, because I know the thing that I did here is I did our standard normal computations. So I want to show you that we could have also done this guy using our X information right here instead. So I'm going to come back and I'm going to redo this second one and show you that we're going to get the same probability here. So let me come back over to Excel here. I'm going to reference these numbers here. This 1.118 is going to matter to me right here because that is my standard error. That is my standard deviation according to the sample distribution here. So coming back into Excel, we could redo this one right here. So I'm going to insert one right here and do this. We want the probability that our X bar is greater than 70.5, which is equal to 1 minus the probability that X bar is less than 70.5. And so here, what I could do, and again, I'm expecting to get the exact same results in here, whether I do the in terms of X stuff or in terms of Z stuff. The Z stuff, I think, is easier to compute a Z-score and then do a standard normal thing in Excel. But you might decide that you think it's easier to do the X stuff in Excel. You can do it either way. So I'm going to do here equals 1. Let me do this. Let me slide this over a little bit so we can see how this here. I know my screen's slightly cut off there. Oh, really? What's that? Okay, that's fine. So I'm going to do equals 1 minus. And now I can do my norm.dist. Notice in this case, I'm not referring to Z, so I'm not doing standard normal. Z is standardized. That's our thing to keep track of there. In this case, my X value of interest is my X bar. That's the 70.5. In this case, the mean of my distribution is 68. In this case, the standard deviation of my distribution is smaller than it used to be. This is the 1.118 that we have computed there, and cumulative is going to be true. And you should notice we're getting the exact same answer. We have some rounding error, so it's getting a little bit of difference out here at like the 5th decimal place, but you should see that these essentially match. This is just coming from the fact that I rounded in my calculator when I did 1.118 is the only reason why we're getting a vague difference right here. I will never care about this difference here. Hey, Infinitesimal Prince, thank you. I'm excited also. I finally made it here today. So notice that there is 2 different ways to do this guy. We can go into standard normal, compute the z-score first, then do a simple Excel computation right there. Not that these are difficult, but I think the standard normals are easier. Or we can do the X stuff after having computed our sample standard deviation there and do a regular norm.dist for that computation there instead. All right. So 2 different ways that we can handle those. And by the way, for you TI calculator people, you should also recognize that in your calculator you also have standard normal computations rather than generic normal. So remember, standard always means Z. Regular normal always means X. Keep those 2 things separate for yourself there. You can either do the work yourself to convert to Z and then do the simple Z probability computations, or just don't go into Z and do the slightly more complicated X computations. But I don't think either of these are really that bad. I assume that you're going to be pretty used to both of these right away. And it's definitely the case that I wanted to talk about z-scores and stuff, because this is just one of those things. Come back over here. I don't need a probability calculator to tell me that it's wildly unlikely that I'm going to see something that's 7 standard deviations above normal or more. I know in my heart that this is an incredibly rare event. We could quantify how rare it is, but seeing the z-score is very meaningful for me probability-wise anyway. 7 standard deviations above normal. That's more than Shaq is above average in height. That's crazy freaking tall. So computing these z-scores first, I do like as a technique here. So where we're going to pick up with this next week is cleaning up the end of section 7.3 of seeing that even if we look at uniformly distributed variables or binomially distributed variables, or the book talks about exponentially distributed variables, which we didn't talk about, their averages, if you take groups of them, the group average will end up following a normal distribution, even though the underlying parent distribution was not, which is crazy. And it's so crazy that you shouldn't believe it until I wrote a little bit of code that's going to demonstrate this to you, and it's going to produce the graphs, and we're going to go from graphs that look nothing like a bell-shaped curve, and they're going to slowly form into a bell-shaped curve as our sample size gets larger and larger and larger. That's the power of the central limit theorem. So that's where I'm going to wrap it up here for this week. And we're going to pick up next week with the closing to this 7.3 stuff. Look at a couple more of these things, wrap up this stuff right here. And very excitingly, next week, we're starting chapter 9, which is starting to get into our hypothesis testing, which is really finally where we're getting to what do statisticians really actually do? They use data to make decisions. We have so far used data to compute probabilities. We want to use the probabilities to make decisions. That's what statisticians do. That's where research and data come together, is decision making. And our decision making processes start in chapter 9 on Monday. So I'm very much looking forward to that. This is it's not like the part of the class that we've done up till now hasn't mattered or isn't important, but this decision making process is really the meat goal of this class, is to make decisions with data. And that's exactly what we're going to truly start with on Monday. We just needed to build up all this understanding of probabilities, of our normal distributions, of our technology use here, so that we can make the appropriate computations, so that we can make the statistical decisions that we want to be making here. So I'm excited that starts next week. So happy week 7, everybody. And I will see you for our next video on Monday. Have a good one.